Good evening to all of you. I would like to welcome all of you on behalf of Electrical and Electronics Engineering Sectional Committee of the IESL. Today's lecture is about lightning protection, and this session has two presentations. The first presentation is about the importance of following IEC standards and adoption of IEC 62305 for our country. And the second part is lightning protection for modern high-rise buildings. Electrical Engineering Sectional Committee thought this is going to be a very useful and timely topic. As you may have seen, there are a number of high-rise buildings are coming up in Colombo and suburb. I will introduce our first speaker, guest speaker, Professor J. Rohan Lucas. I think I don't want to introduce Professor Lucas for any one of you, but as a tradition, I'll do it. Professor Rohan Lucas is an Emeritus Professor in Electrical Engineering of University of Moratuwa. He is also an international professional engineer, a fellow of the Institution of Electrical Engineers UK, and a fellow of Institution of Engineers Sri Lanka. Having graduated with a BSc Engineering degree from the University of Ceylon in Peradeniya and postgraduate degrees from University of Manchester, he has over 40 years of postdoctoral experience in teaching, research, and professional experience in Sri Lanka, United Kingdom, Canada, and New Zealand. He is a recipient of the Jaycees 10 Outstanding Young Persons Award for Academic Excellence, Research Excellence Award, and Teaching Excellence Award by the University of Moratuwa, and the Engineering Excellence Award by the Institute of Engineers Sri Lanka. He has been involved in formulating, inspection, and approval process of Sri Lanka Standards Institution for perhaps 40 years, and he has been involved in recent adoption of IEC standard on lightning protection. Sir, I would like to invite you to present the presentation.
Thank you, Kusala. Okay. So what I'm hoping to talk to you is not technical, but why standards are required. Migor is not here. Okay. The Chairman Sectoral Committee, IESL, Engineer Kusala Peradeniya, keynote speaker Mr. S. Gopakuma, Technical Director OPO Betterment of Germany, members of the IESL, ladies and gentlemen. It gives me great pleasure to speak a few words to you as an introduction to the talk on standards for lightning protection of modern and high-rise buildings. I thought I will start with what most people think is the origin of lightning protection. When Benjamin Franklin flew his famous kite in June 1752 in Philadelphia, thunderstorm. Why did he do this? Because he thought that lightning is charged and he wanted to prove that, and he used a Leyden jar, which you have probably heard about in physics, and part of the string is non-conducting, so that he was careful to make sure that the lightning did not come to him. Most probably lightning never struck the kite. If it did, this experiment would not have been successful. So most probably what happened was the charges in the clouds discharged through the string into the Leyden jar, and he proved this experiment. Many others who tried later actually even got killed. What were the earliest users of lightning protection? Not in 1752. Perhaps much more than 1700 years earlier than that. maybe even in BC. Right. In the ancient times, the only tall buildings were perhaps the stupas in Sri Lanka and the pyramids in Egypt and other places. And in the sea, they were the sailing ships. Sailing ships had lightning protection, and when thunderclouds are charged, you actually see charges given out called St. Elmo's fire. I'm not going to speak any more on that. I thought I will show a picture of some of the taller structures nowadays. Around 2000 years ago, some of the taller structures would have been our stupas, Rohan, Jaycees TOYP and so on. They were of the height order 100 meters. Then you had the Great Pyramid, which was around 150 meters. The largest original brick structures were our stupas. Then you had the Eiffel Tower, Empire State Building. Those also were there long time ago. After that, many other tall structures have come, gradually increasing in height, going up to even over 800 meters. Then perhaps in a year or two, we will also have our own tall structure, the Lotus Tower, which is now coming up in Madalam. Okay. I thought I will speak about some of the ancient lightning protection. They were there in almost all our stupas. How do I know that? Is it hearsay? No. It is documented in the Mahavansa. Mahavansa says that copper plates and silver plates were used at the bottom of the stupa, and lightning protection was used, and subsequent kings also renovated the lightning protection. So they would not have gone on to write such a thing if it did not happen. Why did they do that? Obviously, in the ancient times, the only things which had lightning problems were these tall structures, and they did not want these to get damaged by lightning. So they would have had a method of lightning protection. The Chudamanic at the top of the kota is supposed to be a good conductor, and most probably there would have been some method of lightning discharging inside the stupa. If you go to the beach and you hit something very hard, will the sand break? Sand moves apart. In fact, when I read about the stupa, I was told in the Rohan Sire, special clay was brought from India, and I believe those clay could actually move a little. So when the energy comes, the energy can get dissipated inside. Unfortunately, the Mahavansa is not a scientific document, so it does not say how the lightning protection was done. And lightning protection information was lost because with the ravages of time, the top parts of all the stupas were destroyed. So when we rebuild, we don't really know what was there originally. You can also see the lightning conductor is not seen here. A present lightning conductor is here. The earth wire is running down like that and to the earth here. This is one of the worst things to do. In fact, I have gone with the TRC and even informed the prelate there that this is not a satisfactory arrangement. People think that if you put some sort of lightning protection, it's lightning protection. What is wrong with this? One, if you look at the web, you might find that it says that no stupa in Sri Lanka ever got struck by lightning. Long ago that was true. But when we started adding lightning protection, we brought it out rather than inside. Then the second problem, where is this going? Here. And where do you see the devotees? Right next to it. So if lightning strikes and it goes along the ground, the potential in that region increases and the devotees can get killed. Fortunately, lightning comes with rain, so when it's raining, our people do not remain there. Otherwise, there would have been accidents. And okay, so that's the second one. Another one that was reported in April 2010 was the damage to the Mihintale stupa. Where did the damage occur? At the Pesapallu, not in any of the other parts. Do you think lightning can strike the Pesapallu? Impossible. So how did this happen? You know, our people, especially those who work in the telecom industry, knows the copper tapes on the towers are cut for copper. So what had happened here? Climbing this dome is difficult, but climbing up to the Pesavallu is fairly easy. The copper had been cut at the Pesavallu, and of course no one would have even thought about it. So when lightning strike, all the energy was brought down to the Pesavallu and dissipated there, and you can see what has happened. So if you do something and you don't know what you are doing, you might actually be causing more problems. So that is one of the reasons why standards are very important. Another one, this is Jaycees. You can see a wire coming down. So we like to put lights on these so that during the poor time they are lit. How do you do it? We take a line to the top, put lights, have a generator at the bottom. What happened? Lightning would have probably struck the top. Damage at the top is minimal. But what happened? The induced currents came along the line and burned the generator. So if you do things without using proper standards, that is what is going to happen. Okay, so this is what I was talking about. So if you try to protect something, you must know what you are doing. Otherwise, you might actually cause more harm than not trying to protect it. But these structures are such that the damage that can be done to the structure, the stupas, is minimal. If you go according to modern methods, since the stupas are more than 100 meters tall, you should use not the conical method of protection, but the rolling sphere method. If I use the rolling sphere method, without considering anything else, everything that is shown blue should be protected. So you will have copper all around, and obviously it's a waste of money. But fortunately, the standards also say for buildings more than around 60 meters, you only protect the top 20% of the height, because lightning is not going to come down without striking the top portion. If the thing is more than about 120 meters, then anything more than that height needs protection. So even for side flashes, then the middle part can be removed, only the top portion needs protection if you do need protection. If it is brick and a small portion of that kota gets damaged, I don't think it's such a serious problem. But if you invite lightning to come to the ground, that's going to be much more dangerous. So that comes to what I was going to talk about, basically the need for lightning standards. And at the moment, internationally, only the basic rods and Faraday cage methods are accepted. Any other early streamer methods are not internationally accepted. Then again, why are standards written? So that everyone can't be doing their own research. Research has been done and the best practices have been laid out in standards. Then once you have standards, it gives confidence to those who are going to use those that proper standards have been maintained and damage and so on will be a minimum. A few years ago, that is 2013, the Sri Lanka Standards Institution got together a working group to prepare or adopt standards. Basically what we did was we took our international standards, went through it to see whether they are acceptable, and we adopted these. So these are the standards. SLS 1472 is basically the same as IEC 62305. Unfortunately, the method of giving numbers in Sri Lanka standards, they give their own numbers. Otherwise, we prefer to have a number similar to 62305, so that straight away everyone knows we are referring to the standard. Then we also adopted other standards for low voltage protective devices and for lightning protection systems. I think that's the end of my talk. So the reason why I gave this talk is to tell you the importance of having standards and following standards. Thank you.
Thank you very much, Professor Lucas, for educating us and sharing the knowledge. Let me introduce the second presenter, Engineer S. Gopakumar, Technical Director of OBO Betterment, Germany. Engineer S. Gopakumar is an electrical engineer by profession and a member of various national and international standardizing organizations. He is a director, technical at OBO Betterment, GmbH, and the managing director for OBO Betterment India. He is also a director at LP Consultants International Private Limited, who operates from Malaysia, Middle East, and India. One of the unique consultancy company in Asia providing design and training support for EMI, EMC, shielding, bonding, lightning protection systems. He is involved in lightning protection systems design and engineering since 1997 and has done numerous site studies, projects and technical seminars on lightning protection systems across continents and have wide range of experience in many aspects of civil engineering as well. I would like to invite Engineer S. Gopakumar for your presentation.
Thank you very much, Kosala. So, first of all, I would like to thank the Institution of Engineers to give an opportunity to me to make a small presentation. You know, my presentation is purely from the IEC standard. One moment. So the presentation is basically about lightning protection of, in the printout we gave a modern building, but then we decided to have a small change because modern building is not the only worry. In normal buildings also lightning and protection is a point of discussion. So we made a small change. The purpose of the presentation is to explain you what exactly the current Sri Lankan standards SLS 1472 explains. What is written in the standard? What is important for you? Because all of you buying the standards, reading each and every point and implementing it will be a little bit tough job. Because here we are going to talk about a few of the standards which is already adopted by SLS. But once when we implement for an electrical system for a modern building, you know, modern high-rise buildings, you have the transformer within the structure or within the perimeter or within the RCC structure. So in that kind of a situation, once when we install lightning protection, other considerations also need to be taken into account. For example, where you are placing the transformer, how you are connecting the transformer neutral and body, whether it is connected to the structure, whether it is connected separately, is it grounded separately. So all these points come into picture. I will go through these points which is important for you. Just please treat this as an introduction. I am not going to talk too much about lightning or lightning protection because this subject need sometime 2 to 3 days. So before going into lightning protection, I would like to take your attention about voltage impulse withstanding capacity. Voltage impulse withstanding capacity, you see, every electrical or electronic equipment operating with electricity. Now in this picture you can see, one moment, see here you can see a 400 volt power incoming into a building, 230 400 volt, maybe a sub distribution board, maybe a switch socket, and finally your electronic equipment. Now you see this is the outer wall of the building, and then the building starts. Numbers 1, 3, 2, 1, 2, 3, 4, 4, 6 kV, 3, 4 kV, 2, 2.5 kV and 1.5 kV. These are called as installation categories of a low voltage electrical equipment operating with 400 or 230 volt. Installation category means with respect to voltage impulse withstanding capacity, with respect to voltage impulse withstanding capacity of what is voltage impulse withstanding capacity? Every electrical equipment, electrical device, after manufacturing, the manufacturer should test the voltage impulse or the insulation voltage of the equipment, and he has to declare how much insulation voltage continuously, impulse voltage, this particular device can withstand. I will just show you some examples. So once when you install an electrical apparatus into your building, please note that at the origin of installation, we are allowed to install equipments of installation category 4. At the sub distribution board, the electrical apparatus should be installation category 3 and then installation category 1 and 2. What is this? You see, rated impulse withstanding. This is from the catalog of ABB contractor. Now you can see rated impulse withstanding voltage. See here, this is 8 kV. Another contractor 6 kV. So now the purpose of showing this particular slide is, once when we design a lightning protection system, finally your electrical equipments are only going to be mostly affected due to lightning current flow, and this value is important. That means voltage impulse withstanding capacity of the equipment has to be known to decide what kind of protection is required for your equipment. Just keep this in mind, especially this the particular this figure, because at the end of the presentation, this figure will be connected to the lightning protection standard. Then you will be able to understand the purpose of this particular picture. Now let me go to the lightning protection standards and lightning protection system. Lightning protection, it consists of two: external lightning protection and internal lightning protection. External lightning protection, we are talking about protecting a building as well as a structure. And the internal lightning protection, we are talking about protecting the human being, electronic equipments within a structure, inside a structure. So these two are different subjects. The first subject, external protection, we need to have air termination, down conductor and earthing. For the second subject, we have to have room shielding, safety distances and lightning equipotential bonding. See, once when we talk about lightning protection, people always say, okay, there is a rod or maybe an air terminal, and then the second point which we think is a surge protection device. So generally in the market, people think that an air terminal as well as a surge protection device will do the whole protection. This is a belief all over Asia, which is not true. Air termination, you can see it is a, I don't know, this is not working, I believe. Air termination is only one of the subject. If you have a very good air termination and if you don't have a proper down conductors, then you are in trouble. Most of the buildings in our area, in the Asian countries, the down conductor designs are not proper. In several places we use single down conductor, which is danger. Two down conductors sometimes, which is to satisfy some of the standards. This is also sometimes danger. So depending upon the size of the building, you need the number of down conductors, which we explain later. And similarly, the third point in external lightning protection, earthing system. Earthing, what we generally do is each down conductor is connected to a vertical or a horizontal earth electrode. Is it the right way? Yes, it can be. But nowadays there is no building without electrical or without electricity. Every building has got electricity and electrically operated equipments. And in a building with electricity connection, the most preferred earthing system is to have a ring conductor. A ring conductor means a conductor all around the building. Or the second way is to use foundation earthing. Foundation earthing means the steel reinforcement in the foundation can be used as your earth pit, or it can be used as the earthing system which will dissipate your lightning current. So these 3 points are important with respect to external lightning protection system. The same way, internal lightning protection. Internal lightning protection talks about protecting electrical and electronic equipments inside the building. Once when we talk about protecting electrical and electronic equipments inside the building, these 3 points, room shielding, safety distances and lightning equipotential bonding, all the 3 points are important. If you excuse, I will just connect the collar mic. So, the 3 subjects, room shielding, safety distances and lightning equipotential bonding is important. What we talk about lightning equipotential bonding is During a transient condition, all metallic parts in a building has to be brought to the same potential. All metallic parts in a building means, number one, lightning protection system, air termination, down conductor, earthing, reinforcement of steel in a building, metallic windows, doors and so on, the phase and neutral of a power supply line, copper conductors of a communication or a telephone line. So all these metallic installations need to be brought to the same potential so that there is no potential difference. So if we can achieve a good equipotentialization, all our equipments will be safe. And now the biggest advantage as Sri Lankan citizen, the biggest advantage for you is SLS 1472 part 1 to 4 explains this subject in a very good way. Why SLS is important for you is not only technical part, there is a commercial implication. If somebody want to have the knowledge of IEC, and if you go and buy IEC standard, it's very expensive. Whereas SLS standards you can buy at a nominal charge. So the same subject, in a different way. And you know, surge protection is a part of equipotentialization. It's a part of equipotential bonding. So this particular standard, it has got 4 parts, part 1 to 4. Part 1 talks about general principles, part 2 talks about risk assessment of a lightning protection system or risk assessment associated in a building due to lightning. Part 3 talks about protection of structures and life hazard. Part 4 talks about electrical and electronic system. So the various subjects explained in part 1. General principles, lightning current parameters are explained. Lightning current parameters means basically it starts with how much energy is involved during a lightning. What is the shape of current? In what time, how much time it is going from 0 to peak, and in how much time it is coming to 0 or maybe half. The basic parameters of lightning current is explained with respect to strength of current from how much kiloampere to what kiloampere, and the wave shapes are explained. And in case of strike in a normal building, what will happen, what can happen to a structure, what will happen to a service, and detailed analysis is given. But what is important for you is the last 2 points, lightning protection zone as well as lightning protection level. Lightning protection level is explained in the standard for the purpose of making a risk assessment, or to ensure that you are able to find out the risk involved in lightning in your building. Now we go to part number 2, risk management. Risk management, it talks that the primary thing is tolerable risk. Tolerable risk means under a lightning, out of maybe how many lightning strikes in a particular installation, a failure is acceptable. Let's say a failure of an electrical system. Out of how many lightning strikes? See, before that, 100% lightning protection is impossible for your information. We can only achieve maximum of maybe 99.5 or 99.8% protection. So, in order to find out whether you need protection or not, the risk assessment needs to be done for a particular building. How risk assessment is done is important. We have to know the number of thunderstorm days in a particular area, how many thunderstorms are expected in your area per year, size of the building, height of the building, service connection of the building. For example, you have an overhead line or an underground line, you will have a telephone line, optic fiber cable or copper conductor. So all these parameters are taken into consideration, and finally, this particular standard, SLS 1472 Part 2, gives you an indication whether you need lightning protection or not. If you need lightning protection, up to what level you need, whether you need a very strong protection or maybe a little bit lesser protection, is also explained in this particular standard. So you can also understand how lightning is assessed. Assessment of risk due to flashes to the structure, flashes near the structure, flashes to a service line connected to the structure. These are explained in the standard. Then we go to part number 3. Part number 3 talks about class of LPS and design of LPS. What is class of LPS? Lighting protection system in a particular building is divided into 4 classes. Class 1, 2, 3, 4, or lighting protection level 1, 2, 3, 4. The strongest one is level 1 and the lowest one is level 3. So these 4 levels or 4 classes are explained in the standard in order to find out if you need a lighting protection system, what level you need, the strongest one or the smallest one. Because finally lighting protection is connected to economics, money. Whether you have to spend less money or more money. If you spend more money, is it worth? So all those points are explained in the previous slide with that part number 2. If you go through it in detail, you will get a very clear idea. Now we talk about the part number 3. Part number 3 talks about external lightning protection, air termination system design, down conductors, earth termination, and components, materials, and dimension. Very important for you. Whether this particular chapter, components, materials, and dimension, it explains you whether you need to use steel or copper or aluminium, under what condition, what are the dimensions which you can choose, whether it's a flat conductor or a round conductor, what kind of connections are required, are explained very well in this particular section of the standard. The standard also talks about lightning equipotential bonding and electrical insulation of external lightning protection system. Imagine you have a building and at the top of the building you have an air terminal, let's say maybe several air terminals, and there is a chiller, say an air conditioner chiller. Generally what we do is we put a rod maybe little bit away and then calculate the angle, and if the angle is sufficient to protect against a direct lightning strike, we believe that okay, now the chiller is protected. This is only one part of protection. The second part is how much electrical insulation, how much distance, what is the distance required to avoid a flashover from your rod to the chiller. You imagine that this is a chiller, and now we have put a rod here, which is connected to other parts of the building. How much distance is required to ensure that there is no flashover from the rod to the chiller? Is also explained in this particular standard. Various calculations are given, and if you wanted to have an exact, very good lightning protection system, each and every calculation need to be performed. Part number 4. Part number 4 talks about the design and installation of LEMP protection measures system. You know, LEMP, lightning electromagnetic pulse. It is becoming a very important subject once when we talk about protecting electronics, sensitive electronics. Lightning electromagnetic pulse can directly kill a sensitive equipment. It can make trouble to all the electrical systems. So in this particular part 4, the standard explains how LPMS is designed, the lightning electromagnetic pulse system is designed. Design of LPMS, lightning protection zones, basic protection measures in LPMS, and the second part talks about earthing and bonding. Please understand, earthing is not the only subject. Earthing and bonding. Earth termination, bonding network, bonding bars, bonding at different boundaries in an LPS is explained. Then magnetic shielding and line routing. What kind of magnetic couplings can happen during a lightning strike? How you have to route the cables are also explained. So now going to the first slide about the energy of lightning. What is explained in this standard is lightning consists of a primary strike, main discharge, and a time. After that, one or several secondary discharges will be there. To protect an installation, what is important is we need to know the amount of energy which is involved in the main discharge. Main discharge, you see, current is going from 0 to peak. It is also flowing for some time. The peak current in kiloamperes as well as the time is explained in the standard. With respect to time, energy equivalence of lightning strike is calculated as 10 by 350 microseconds. 10 by 350 microseconds means the lightning current goes from 0 to peak and comes to half value in 350 microseconds. This orange line. It doesn't mean that lightning is always following 10 by 350. No. Lightning will be maybe maybe 100 by 1000 or whatever it is. That is not the point. The point is to protect the building. Once when we design a lightning protection system for the building, we need the components like conductors, connectors and so on. How these components are tested is more important. The equivalent energy wave shape given in the standard is 10 by 350 microseconds. You know, this particular part, this 10 by 350 is important for you, especially once when you buy components. You know, worldwide, once when you want a surge protection device for the power incoming into a building, you imagine that in your house there is a power incoming distribution board and you want to buy a surge protection device for that incoming power supply. In the market, you can see surge arresters with 40K, 50K, 100K, 200K, 400K, 600K. But generally, nobody explains the shape. So, for the mains incoming panel, you need an SPD which is tested with 10 by 350 microseconds. Then we come to the current later on. So, there is a main discharge and there is a secondary discharge. Both are evaluated very well in the standard and the designing is done. Now, once when we talk about lightning protection, we are talking about two wave shapes. One is 10 by 350. There is one more wave shape which is explained, is called as 8 by 20. 8 by 20 wave shape is the energy equivalent of a transient surge, maybe a switching surge or a surge which is created due to coupling of a partial lightning current. Source of damage. What are the sources of lightning which can damage or which can create problem to the building? S1, source 1 is lightning strike, a direct lightning strike on the building. Source 2 is a lightning strike very close to the building, because in case of a lightning strike very close to the building, you can see that this particular S2, due to the potential rise, all electrical apparatus which is connected to ground will experience a high potential and there will be flash out. S3 is a direct lightning strike on the service, and S4 is a lightning strike which is near to the service. These are the four parameters, or these are the four kind of lightning strikes which can create trouble to us, which can create failures. And this is actually a simple way of explaining the lightning protection scenario. You imagine there is a lightning strike in a tree near to your building. Whether it is S1, S2, S3 or S4. Lightning strike in a tree near to your building comes under S2. So, all the four parameters are explained here, and the first point with respect to protection is estimation of the damage in case of S1, in case of direct lightning striking a building, let's say particularly this particular building, what can happen? In case of S2, what will happen? In case of S3, what will happen? In case of S4, what will happen? So all these are evaluated with this particular chart. Depending upon the frequency of lightning, place and environment of the structure, size of the structure, number of people inside the structure, and finally risk of injury and loss of human life. That means in case of direct strike, this particular damage, maybe a fire can happen, and in case of fire, the size of the building and people inside the building are important. So what kind of risk is associated is also studied in the standard very well. And now basically the standard says you can have based on this the risk as well as protection required, you can divide the lightning protection into 4. 1 is the high and 4 is the lowest. Lightning protection level 1 to 4. See the first one, peak current values of lightning strike. In the earlier one which I have shown, 10 by 350, that is the shape of current. But how much kiloampere it can go? The first one, the first line shows lightning current can go to any value. The maximum recorded lightning is about 400 kiloamperes. But for the purpose of protecting a building, maximum lightning current considered in the standard is 200 kiloampere. Now the second line, 3 kiloampere to 200 kiloampere. Third one, 5 to 150, 10 to 100, 16 to 100. These are the various lightning protection levels explained. Level is nothing but if you want a protection class 1, that means your building is protected from a lightning from 3 kiloampere up to 200 kiloampere. If you are going for class 4, your building is protected from 16 kiloampere up to 100 kiloampere. So this classification is important because once when we go for higher and higher current, that means from 100 kiloampere you want 200 kiloampere, the problem is you need a lot of shielding. You have to create a Faraday cage, eventually a big Faraday cage in your building. You need to have space between your outer wall and your electronic equipment. So all these things will increase the cost. So the standard gives a proper way to find out what approximate protection class is required for you. See, once when we make, once when we go for a site study or once when we make a real installation, some of the points which we always discuss, I want to explain. For existing building, we can only have an isolated lightning protection. Isolated lightning protection means, say for example a down conductor which is coming. The down conductor has to be placed on the wall. It is not integrated inside the wall, it is placed on the wall. For example, this particular stupa, you explained that. Maybe earlier days, the down conductor is inside and the belief is there is no lightning strike because there is no failure. Once when we made it modern and put it on the outside the structure, isolated from the structure, then copper is stolen and then the other issues, problems start. So now, isolated lightning protection means a lightning protection system which is not connected to the structural steel. It doesn't mean that it is isolated 1 meter or 2 meters away. No. Isolated lightning protection means a lightning protection system which is isolated or insulated from the structural steel. And the second point, lightning protection using structural steel. This is the best method. The best lightning protection system you can achieve if you integrate your lightning protection, especially down conductors and earthing, into the structural steel. What I mean is, most of the modern buildings or most of the buildings which we construct nowadays have steel reinforcement. If you integrate the steel reinforcement or if you connect the steel reinforcement as a part of lightning protection system, you will get the best protection. So today's seminar is basically to explain you how and where you can integrate, how can you connect your lightning protection system to your steel column or steel reinforcement. This portion we are coming in the next slides. So just for your information, the best protection is to use the structural steel, which will offer the best protection for electronic equipments especially. Now you know, whenever we go for an assessment of an installation, the problems which we face is single down conductor, which is quite common in several parts of, especially in India. In several buildings, one down conductor, sometimes two down conductor for a large building. If we explain that, look, you are doing a mistake, two down conductors will not do, maybe you need 5 or 10, but then the first argument comes, no, my architect will not allow. My architect don't want to show a down conductor outside the building because it do not looks nice. So then what people do, you know, in lot of places, I have seen, including my building which I live in Chennai, down conductor is routed through the electrical shaft, which is really deadly. This building, my building is about 120 meters. The electrical shaft is maybe 5 meter wide and about 2 meter width and about 6-7 meters long. And through this shaft, down conductor, 2 numbers of copper down conductor is routed. Okay. Now, such installations are quite common, and this kind of installation, it will only satisfy some of the rules and regulations. It will not give any protection. You can be sure. So, single down conductor as well as bending is quite common. So, you can be sure that one down conductor or two down conductor with lot of bends is a disaster. Also, once when we talk about earthing, the knowledge of ring earthing as well as the knowledge of using foundation earthing is missing in some parts of Asia. In some places, if we talk about you have to make a foundation earthing, then the argument starts. No, my structural engineer will not allow to connect the reinforcement to my down conductor or earthing. Because what people believe is, if you have a down conductor, maybe 2 down conductors and isolated from the building, away from the building, then the current flows. So my structural engineer will not allow to integrate the lightning protection into the structural steel. This is also a big argument. We have additional information, and not we. The standard explains lot of ways to convince your structural engineer why you have to have a connection between reinforcement and your down conductor, and at what condition is also explained. Anyway, I will go into it in detail. But basically, if we explain to a customer that, look, you are going to construct a new building and you need to use your structural steel as part of lightning protection, generally 80% of the customers, they don't accept. Then we have to go with the standard and we have to show to them and we have to explain in detail. But anyway, I am coming to that point. So direct or indirect connection to structural steel to avoid flashover and fire. So this is also explained later. Length of connecting wires of SPD. You know, nowadays, last 5-6 years or maybe last 10 years, the knowledge of SPD, surge protection device, it has become common. Engineers know what is an SPD and what it does. But unfortunately, what we do is, in several cases, SPDs are connected with long wires, which will finally don't do the job, and lose connections and flash over. So here, LPS design, lightning protection system design, from the standard, this particular chart is from the standard. It explains how a lightning protection system need to be designed. I don't go into detail because I think the printout is clear. Part of external lightning protection, air termination, down conductor and earthing, and a little bit wound shielding. And what is happening? In case of lightning strike, the current flows and a high potential is created. In several parts of the world, several countries, people believe that current goes to earth. And they try to put deeper and deeper earth electrodes because current goes very much inside the ground. This is the belief, but this is wrong. Lightning current flow is a surface phenomenon. Current always try to flow through the surface. Lightning current always try to flow through the surface. And in this particular case, direct lightning strike in a building, it is calculated in the standard that approximately 50% of the current goes to earth and 50% gets into the building. 50% of the current can flow inside the building. Under what condition is explained. So now, air termination. There are three methods explained in the standard. One is a rod, which is offering certain angle of protection. I don't know about the older CEng standards. Whereas in some places, for example, India, the old standard says protection angle is always 45 degrees. But now, what is explained in the standards? Here you can see alpha 1 and alpha 2. See here, the protection angle at one side of the rod and the other side of the rod. And alpha 1, or the protection angle is less at one point of the building because the height is more. The height of the place to be protected is more. So the angle of protection depends upon the height of the building as well as depends upon the class 1, class 2, class 3, class 4. Whether you need 200K, 150K or 100K protection. The second protection method is mesh, lightning air termination mesh. In simple, you can have a rod in the top of the building which offers an angle of protection. If you have a large building, you need to have several rods. The second way is to have a mesh at the top of the building, which is one of the easiest way. And the third way of protection, which is not explained in the standard, is to have a catenary wire. In large substations to protect the transformer, sometime, or not only in substations, sometime in oil installation, refineries, petroleum storage installations. So, to protect a tank, two structures are erected and a catenary wire is connected at the top, which will give certain angle of protection. These three are the normal methods of air termination, but more and more in the standard, a rolling sphere is explained. Rolling sphere means energy equivalent of a lightning strike is electrogeometrically explained as a sphere. I don't know whether you understand. The energy equivalent, that means you for simple calculation, you imagine that 100 kiloampere per lightning strike. It is equal to maybe this size ball. And this particular sphere is rolled over the building. It is rolled over the building. It is like a ball. It is going from one side to the other side of the building. And wherever the ball touches, there is likely a chance of direct lightning strike. Say for example, in this particular case, you can see if we roll this particular sphere across the building, from here it starts. This place is not, it won't touch, it is a protected place. From here onwards, it will touch the building. Throughout the surface it will touch, and maybe again something like this. What does it mean is, for this particular value and for this particular building, from let's say this point where I am keeping the mouse up to this point, there is a chance of a direct lightning strike. Rolling sphere will not give any protection. Rolling sphere will only give an indication where a lightning can go and strike. So now, to protect that particular area, either we need a rod, or we need a mesh, or we need a catenary wire. So three ways are explained here. See here, a rod which is offering, let's say, this protection, less protection, and the same rod offers a little bit bigger angle of protection. See, this is the angle, bigger angle of protection, because here this part of the building, the height which we need to consider is less, and at the outside height we are considering is more. And mesh method means, you can see at the top of the building there is a mesh, and normally the mesh has to be at this place also. So something like this, and the size of the mesh is explained in this standard. So remember, any structure, any building, most important points to be protected are corners and edges. So the protection, air termination or down conductor, first we always should design the system in such a way that lightning will probably goes to corners and edges, which I don't want to explain. I don't want to explain why, but basically corners and edges are more important. So now, if you have a PE building, pre-engineered building, or a steel structure which is having a sheet, steel sheet at the top, do we need an air termination? This question is, we can argue in several ways, but generally, if your steel, if your roof is thicker enough to handle the energy effects, you don't need an air terminal, because the sheet itself is a good conductor. It will take care of the lightning current, provided it is connected to the ground. You can see in this particular case a building with a steel roof, and this particular steel sheet at the roof may be enough, provided it is connected to ground through steel columns. Metallic frames, so what basically the standard says is, in case of this kind of a building, under certain conditions, you don't need an external protection. Under certain conditions, it is underlined. You don't need an external protection system. What can happen is, in case of lightning strike, your electrical apparatus will be in trouble. That needs internal protection. It is nothing, it is not connected to external. So, modern factory buildings, most of the factory buildings or industrial buildings nowadays, roof is steel, wall is steel. In this particular case, in this picture, you can see a building with a steel wall, which is simply connected to the reinforcement. So here, one more please. So this is the connection, braided connection of the steel sheet, which is nothing but the steel wall, and the reinforcement. this kind of a connection at several places will do the job. In simple, you don't need a down conductor for this kind of a building. If you provide a down conductor which and sometimes may be insulated with a small bush which is of no use. I don't know what is done in Sri Lanka, but in several places what engineers do is, even if the building is steel, down conductors are running with a small insulator. Because this will not do the job. What is required is you need to connect the steel as a part of your production. One of the slide which I have missed purposely here is see, I explained angle, mesh and rolling sphere. Also I explained the lighting production class 1, 2, 3, 4. Angle of production depends upon the height as well as the class of production, but where it is shown, I have removed that slide purposely because if you are interested to know it, just Google it, you will get the value. Just find out the angle of production which is explained. Now regarding down conductor, here also the value is missing. You see there is a chart at this place which is removed. Just to give an information to you that, because if I try to explain everything to you, then you will not refer to your standard. You will only use my note. I don't want to give wrong information. So please go through the standard and find out the number of down conductors required for a building. See, for a particular building, at every place, you see one down conductor here, next down conductor here. In the top line of the building, this particular building has got 6 down conductors. What is the purpose of having different conductors, different or number of down conductors? One of the prime objective is a building with more number of down conductors, lightning current will flow through several parts. Magnetic effects of lightning is reduced. Once magnetic effect of lightning is reduced, electronic equipments are safe. In simple, for this particular building, if you have one down conductor, at the event of a lightning strike, the whole current, this heavy current, maybe 100 kiloampere or 200 kiloampere, 10/350 microseconds, this much energy will flow through one conductor, and that current flow is enough to destroy your electrical equipments, electronic equipments. Instead of one down conductor, if you have 6, then the current is divided into 6 parts. Current through each conductor is less, magnetic effects are less. I hope you understood the down conductor part. Any questions? Yeah, thank you. But I would like to ask one general question. Are you able to understand my language? Because normally in the presentation, I used to interact in between and people are laughing and some questions used to come. Whereas here, it's totally silent. Yeah?
We will get questions after this.
Okay, thank you. So now, the best way of protecting modern electronics is to use the reinforcement of the building. Because modern buildings, multi-story buildings, definitely this is steel reinforcement is used. And this reinforcement can be connected as down conductor. Say for example in this case, I'm sorry that I don't have a pointer. No, does it have a pointer? Oh, it is there, yes. See in this particular case, you see here, this red line from top to bottom, it is nothing but maybe a column. Or the steel inside a pillar. steel inside the top slab, and you see this particular place where the reinforcement is taken out of the building. It is taken out of the building and then it is connected to number 2. Number 2 is nothing but air termination. It is connected to a mesh, and then a small portion is connected to this particular to protect the parapet. If we explain this system to civil engineer, then the next fight starts, because civil engineers or the structural engineers, they will never allow. I'm sure some civil engineers are also here. If some civil engineers are there, can you raise your hands? Do you accept this? No. It is. Yeah. 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 So, yeah. So now, once when we talk about this, that means I am explaining to the architect or to the civil engineer, to my structure with this particular pillar, steel in this particular pillar has to come out of the structure. Then they don't agree because of corrosion. Because a small corrosion of this particular conductor will spoil the whole building, because we are designing the building for next 50, maybe 70, 80 years. So this is not a good engineering practice as per the civil engineering rules, but there are some ways. In simple, for protecting electronics, this is the best, but this particular place, you need the expertise of a lightning protection expert. You need to have some special, you need to do some special things to ensure that your structure is not corroding because of an air termination system. Now, you see here, this is the, for a modern building, this is the supposed to be the down conductor, and what is recommended in this standard is a strong connection at every 5 meters. This distance C is 5 meters, and the small distance is B. So this connection, every 5 meters, you need to have a strong connection with a clamp or with a welding tested to withstand that particular lightning current. I hope you understood. So you can use the steel reinforcement, provided you have to take care of the connection between the places, the steel inside the concrete to an outside object. So, because corrosion. The second point is with respect to strength. Every 5 meters you need to have a clamp or a welded joint which is tested to withstand partial lightning current. And every 1 meter you can have a normal connection with the right side. So, and now the most interesting point number 5. See, please understand, this picture is not my picture, it is from the standard. Part 4, it is from the standard SLS 147 part 4. And now look at the point number 5. Point number 5 is equipotential bonding bar for the internal lighting protection. You know very well that we have, for a low voltage energy distribution, we use TN, TNS, TNCS, TT, IP, and different kinds of energy distribution systems are there. That part anyway I am not explaining in detail because that is totally a different subject. If we consider a modern building, what I mean a modern building is a large building, multi-storied building with maybe one or several generators and transformers within the building, within the structure. In those kind of installations, the 5 can be the PE conductor, the earth conductor for the whole building under several conditions. But this is a modern way of reducing the cost of electrical installation. This is my border, I don't cross, because then the subject is a whole confusing. So just for your information, please please understand that the earth termination for this particular the earth termination for the whole for the whole this particular floor is from point number 5, and point number 6 is a test joint, and this particular point number 6 the test joint and the area outside the test joint. Look at here. People think that this is for the earth termination, for dissipating the current. No, this is for the purpose of reducing the step potential to protect people outside the building. For example, you imagine that this is the building. During lightning strike, high potential is created because of dissipation, the current dissipation to the ground. And what will happen to a person who is standing at this place? So you imagine a person standing like this. No, my picture is not very accurate. Sorry, because of the pointer. Yeah. So due to avoid a step potential, say imagine a hospital or a school. Imagine a school or a hospital. The building is protected. Electrical systems are protected, people inside the building are protected. What will happen to people, those who are outside the building? Direct lightning will not strike because the structure itself is tall enough to protect the persons. But this current flow through ground, remember, surface phenomena, more step potential is created. Step potential is nothing but the potential difference between the steps, and that can create accidents. To avoid step potential outside the building, structural steel need to be extended outside. So there is a clear picture in the coming slides which will give you a clear picture. So now basically what is required is, I hope my sound without speaker is enough. What about, you can hear? Okay or not okay? This is good. Yes. So, in this particular case, you imagine a building which is very close to the main road. That means you cannot extend and you cannot place a ring conductor on the road because the authorities will not allow you. In that case, this particular the steel foundation is enough to dissipate the lightning current. Again, under some condition. One of the conditions is, most of the high-rise buildings, the parking area is underground. Level 1, level 2, level 3, level 5, and sometimes even up to level 8 levels under the floor. Generally, in those buildings, between the soil and RCC, a thick plastic sheet is provided to avoid water seepage. So, if let's say this is a water insulation, if water insulation with a plastic material is provided for this particular building, will it dissipate the current? No. So, this is one of the conditions. So, in that particular case, we need to have an extended external ring conductor. I hope you understood. So basically, a building without insulation against water, that means a plastic sheet, a building without insulation against water, you can use this particular method. That means foundation ring itself will do, the foundation earthing electrode will do the job. This picture is also from the standard equipotential bonding within the structure, the previous picture, but in a better way. You see here, you have an antenna which is connected to the structural steel in the slab. Equipments are connected to this particular this is in the previous slide it was 5. That means the equipotential bonding for bar for that particular flow. And from that bonding bar, a PE conductor is running, which is connected to every equipment. Finally, the equipment is also connected to the reinforcement through the other side. So, basically, in this kind of an installation, electronic equipment will get a very high protection against LEMP. LEMP, lighting electromagnetic pulse. Just for your information, you imagine that an apparatus which is here and this place is not connected. I mean, the connection number 4, a bonding connection between the apparatus, the PE conductor and the reinforcement. It is not connected. What will happen? Depending upon the sensitivity of the equipment and the PE conductor length and the power line conductor length, there can be loop currents which will destroy your electronics. So to make a 100% perfect installation, you need to refer the other standards, the EMC standards 61004 series, which explains this phenomena in a better way. So another problem, another advantage of this particular installation is, see in the top, you have an antenna or you have an electrical apparatus which is connected to the reinforcement. You imagine that there is no connection here, this particular point number 4. How to protect the antenna against flashover from the building? The same question she asked. There is a rod near the antenna. From the rod to the antenna, there can be a flashover, and how to avoid it? One of the ways you connect it together so that there is no flashover. Number 2 is you keep it away from the lightning protection system. You calculate the distance, safety distance required, separation distance required, and you keep it away. So now the point for you is, if you make use of this yield reinforcement, you can just avoid the safety distance. You don't need to calculate. You don't need to complicate the total design. Other questions are listed here. What kind of low voltage network you are using? Connecting the neutral in the MV and the LV transformer. Are you connecting the neutral and the body together, or everything is separate? Whether it is connected to reinforcement? All these questions also need to be considered while you do an installation. I will explain you some of the standards. For example, I just downloaded the standard. Say IEC 60364. 60364 is the series of standard which explains how to design the low voltage or electrical network. It consists of several standards. Totally, I think about 70 or 80 standards. Part 1 talks about fundamental principles, assessment of general characteristics, and part 444. Protection against voltage disturbances and electromagnetic disturbances in the electrical installation of a particular building. It is explained in this particular standard 60364 444 and 60364 554. It talks about what kind of protection devices and how to erect, selection and erection of electrical equipment for isolation, switching and control. This standard also need to be considered. 60364 554. Selection and erection of electrical equipment, earthing arrangement and protective conductors. I hope you are able to understand. All these standards, the conditions given in all these standards also need to be considered while designing the lightning protection system for a modern building, and you can be sure that you can avoid almost 100% failures. Even if the standard says 99.9% efficiency, you can be sure that failures will be totally avoided. Another question is, see the 61936 talks about power installation exceeding 1 kV, common rules. So this standard gives an indication whether the neutral and transformer body need to be separate or connected together. If it is connected together, what kind of LE network you have to have, what kind of protection devices you need to have. All these conditions are explained in the standard, and the standard also explains under what condition you can do a connection of this. I hope you understood. Basically, to achieve a good protection for a modern building, you need to connect steel reinforcement. You need to use steel reinforcement as a part of lightning protection system under these conditions, under satisfying these conditions. So, once when we say, I explained to you, every 5 meter you have to have a strong connection. These are the conditions. The first three pictures, first three lines, 1, 2, 3. So these 1, 2, 3, these are the conditions which we need to ensure, or these are the things which is ensured in the standard, which is supposed to handle partial lightning current. That means every 5 meter you need to have this kind of a connection, either a welded connection, the overlapping distances are explained, or you need to have a, say for example a clamp like this, tested for lightning protection, or a bright connection which is very difficult to achieve in a place. And every 1 meter you need to have this connection, a normal connection with the braided wire. So you know, normally in a building this is very easy to achieve. If the civil engineer is knowledgeable, this is quite easy to achieve. One of the example. Once when IEC recommended this practice, that means you use your reinforcement, you use your structural steel, then the argument starts. Structural engineers will not accept, because then you are doing something to the structure which is giving the whole strength of the building. So then, as a solution, it is recommended in the standard that you can also run a separate conductor. You see here, there is a separate conductor. So this separate conductor also will do the job of a down conductor, or all the previous conditions can be skipped off. So this is just an example, especially for isolated down conductor. Isolated down conductor means which is for an existing building, a down conductor which is outside the building with this kind of a bend. You imagine this kind of a bend. Say most of the buildings with a parapet, or sorry, with a above the ventilation or above the window, you have the kind of a cantilever. So there we used to take this kind of a building, and it is a kind of a disaster during lightning current flow. Electrical insulation. So this particular slide, it explains what kind of safety distances need to be maintained. So you cannot, again this picture is applicable only for existing buildings where you are not using structural steel. If you are using structural steel, then delete it, you don't need to consider. If you are not using structural steel and if you have a down conductor outside the building and an electrical apparatus inside the building, we need to very clearly calculate the safety distance, and either the down conductor need to be removed or the apparatus need to be kept away to avoid direct flashover from down conductor. Now we go to down conductors, earth termination. Earth termination. There are two types of earth termination explained in the standard, type A and type B. Type A, it is isolated from the building, maybe a vertically driven rod or a horizontal conductor, a horizontal electrode or a vertical electrode. Type B, a ring ground electrode and foundation electrode. So for buildings with electronics, This is the only recommended way. Type A is recommended for small houses or small buildings without electricity connection. How many buildings we can see this kind of a building without electricity connection? Almost nil. So generally, this is what is required. Type B, either a ring conductor or a foundation earth electrode. If you are using a type A, the next argument is what is the electrode resistance, the earth resistance. The maximum value recommended in the standard for earth resistance is 10 ohms. It is also not a condition. One of the conditions is you have to have 10 ohm earth resistance, and the second condition is the 10 ohms can be skipped under this condition. For example, LP lighting production level 1, level 2, level 3 and 4, and x-axis you can see the soil resistivity, and this is the length of the electrode. You imagine you are going to have a building with level 3, class 3 protection or class 4 protection. What is recommended in the standard is about 5 meter or maybe 6 meter long conductor in contact with soil is enough to dissipate the current. And if you go for higher protection, then you need to have a longer earth electrode. This is only for type A. This is interconnection of type A, how to achieve the type A earthing. I skip a few of the slides because we have so many other things to discuss. Yeah, this is about the ring electrode. I asked a question, how to protect people outside the building? Generally we don't consider. Protection of people outside the building against step potential is also equally important. One of the methods explained in this standard is, and this you cannot find in the standard, it is not from the IEC 62305 standard. I showed you some other standards. So you have to go through those standards, and soil equipotentialization is also required. Soil equipotentialization is nothing but a simple way of making equipotentialization of the soil around the building where people movement are more, or where you need protection against step contact. So here the method is, you see, there is a ring conductor. This is a ring conductor. The first one is 1 meter away from the building and a half meter below. The second ring conductor is 3 meters away from the first one, but 1 meter below. Again 3 meter, half meter more down. Again 3 meter, half meter down. So this way of making soil equipotentialization will protect people outside the building. Why I showed this is, if you are using lighting protection, or if you are doing lighting protection especially for schools or playgrounds, so this point need to be considered. I skipped few. Example of a foundation earthing. I told you that foundation earthing is the best way, but you need to, the engineer, the civil engineer need to think about it, and you need to incorporate during the foundation construction itself. So in this particular picture, you can see the reinforcement before casting. And here there is a connector, a special connector, which is to connect between the steel reinforcement and an outside component. This is a critical point. This is a special connector. You can see here. So this one is the wood, and the way of connecting the reinforcement. And you see, in a building, foundation earth with a strap conductor. So this is the complete foundation, but the additional strap conductors are ready every, I think this is about every 5 meter or every 10 meters. Some values are given in the standard. And this whole mass, steel mass, will do the job of dissipating the current, provided, as I explained earlier, there is no insulation between the foundation and the soil. Examples of photograph. Some photographs, you can see how this slab conductor is connected. Another case. So this is an example. Example of connecting earth termination to lightning protection system in case of natural conductor. That means in case of using the steel reinforcement, how to connect the structural steel with an outside, maybe a soil equipotentialization. There are certain conditions given. The conditions are explained here, but each condition there is an explanation which also need to be considered. Foundation earth design depends on the type of foundation. What is explained is, see this, isolated foundation with the foundation earth electrode in non-reinforced concrete layer below the bitumen insulation. This is also from the standard. You see the what? And this black and white, the point number 1, it is down conductor. I think there is some mistake. It is not point number 1, it is 7. Damp proof membrane, watertight insulating layer. So from here I thought it is number 1, no, this is number 7. So this is the insulation, water insulation which is provided. And in this case, you have to think of extending the earthing, and one of the methods is under the building, under the insulation you can have a mat. So this is another way. This is another way. Under the mat there is a kind of an RCC installation. So different methods are explained, but once when you design this kind of a building, you need to really buy the standard and go through it. Bimetallic corrosion. All of you knows very well. This is also a big problem, problem in most of the installations. I skip this. Okay. Now, whatever I explained is only just giving a kind of a small introduction. Don't think that this is the whole. The whole, to study the whole lightning protection system, it needed 2-3 days. But whatever I explained to you is just an introduction. And the second part of lightning protection is internal lightning protection, protecting electrical and electronic equipments inside the building. So here the subjects are lightning equipotential bonding, room shielding, safety distances, and self-protection is a part of internal lightning protection system. Why self-protection has become important now? Because we use the disturbances in our network is increasing day by day, and on the other side, this picture shows in the early 1950s we were using vacuum tubes. That means there is enough space between two terminals, more insulation, it can withstand more insulation. Whereas now we go for large scale integration, very large scale integrated circuits where the insulation levels are very low. So since the disturbance is more and insulation levels are very less, you need surge protection. Remember the first slide which I shown you with this green graph, class 4, class 3, class 2, class 1. IEC made this standard in order to ensure that the manufacturers are not reducing the sizes again, compromising the impulse standing levels. Okay, skip this slide. What is important for you is coupling voltage in a distant lightning strike. See here you can see a building with a lightning strike which is approximately 2 kilometers away. What will happen to this particular wiring conductor loop due to electromagnetic effects of light. Once when the electromagnetic force flows through air, this electromagnetic force will induce surges in the conductor loop. So the previous one, this is a conductor loop with nothing but from the main distribution board, the wire is going to some distribution board and finally to the computer. There can be surges induced in this particular wire which will destroy the computer. How to protect against this? The first one is, reduce the amount of radiation which is influencing the electrical wiring. That means this is the building, 2 kilometers away you are going to, there is a lightning strike, magnetic force is flowing over the area and we have sensitive electronic equipments inside the room. How to shield the outer wall of the building is the question here. Now the simple answer is, if you integrate structural steel, the whole building acts like a kind of a Faraday cage. And your equipments, the influence of magnetic influences inside the Faraday cage is naturally reduced because of the Faraday cage. So a building without connecting reinforcement, maximum surges will be induced in the electrical wiring and your equipments will be destroyed. So it is very important that to avoid the failure of electronic equipment, you need to connect reinforcement, structural steel as part of lighting protection. Excuse me, Mr. Kosala. How much time more is available?
Very limited.
Very limited. Maybe 5 minutes or 10 minutes?
Yeah, you can take 10 minutes. So we need some time for the question and answers.
Okay. So I hope the explanation of this slide is understood well. Do you have any question on this particular slide? What I explained is, in a distant lightning strike, electromagnetic force will flow over the area which will create surges in the conductor loop. One way of protecting the electronic equipment is reduce the influence, electromagnetic influence, this red semi-spherical lines, reduce the influence of electromagnetic force. One of the way of reducing the electromagnetic force is to create a Faraday cage in the whole building. And to create a Faraday cage, the best way is to interconnect the structural steel in the previous, which I explained in the previous slides. So, once when we talk about the internal lighting protection system, what is important for you is setting up a protection zone. Lighting protection zones in a building, setting up equipotential bonding, shielding measures, installation of protection components. These are the 4 subjects which need to be considered. What is lighting protection zone? A building to be protected is divided into various LPZ. LPZ 0, LPZ 0A, LPZ 0B, then LPZ 1, LPZ 2 and LPZ 3. You see this area, LPZ 0A. LPZ 0A is an area outside the building where a direct lighting can strike this red area. A direct lighting can strike in this particular place. So 0B, direct lighting will not strike. For example, this side of the building, direct lighting will not strike on that area. Instead, it will strike the parapet or it will strike the air terminal. But this is also a dangerous place because partial lightning current will flow through the area. If you have a down conductor, lightning current is going to flow through the down conductor, which is not allowed inside. It is outside the building. Lighting protection zone 0B. LPZ1 is the assumed outer wall of the building. It is a place, it is the outer wall of the building. And an inner wall of the building can be assumed as lighting protection zone 2. Metal case of a server, for example, metal case of a computer can be assumed as lighting protection zone LPZ 3 or LPZ N, any number. So now, how to achieve lighting protection zone 1? So, to call an area inside, you imagine that this building and this is the outer wall of the building, and I want to call this place where I am standing as LPZ1. What are the conditions? Condition number 1 is magnetic influence in this area shall be reduced. It is, you cannot have a big amount of magnetic radiation. No, it has to be controlled. It has to be reduced. Conducted surges through lines means potential difference. Transient currents, transient voltages through lines need to be reduced. Equipotentialization need to be achieved throughout the wall, throughout the first place. You know, I am trying to explain it in a technical way, but practically applying it is different. So, if we are able to achieve the several conditions stipulated, we can call that this particular place or the place where I am staying is a safe place with respect to lightning, because magnetic forces are less, radiated surges are less, conducted surges are less, and I am able to withstand. Please remember, I am able to withstand. It doesn't mean that nothing comes in. No. The disturbances are limited so that the equipment is able to withstand. So, in order to ensure that, you imagine you have a big, an air circuit breaker or an MCCB, which can withstand a higher impulse voltage. That is one condition in a building. The other condition is you have a very sensitive electronic equipment. So, building is divided into various zones to ensure that the place where you are installing an MCCB, the same maybe a PC, cannot be installed. So, you need to have different zonals, and basically every zone boundary means an equipotentialization and a reduction of conducted and transmitted radiated surges. So this is, I skipped that particular slide because current flow 50% goes to ground and 50% gets coupled into the building, and what we need to do is this 50% which is coming inside need to be diverted through the services. So, other condition I told you, in order to call this area as lightning protection zone 1, that means the green area as lightning protection zone, one of the conditions is requirement class 1 and 4 kV. The maximum amount of transient voltage allowed in this place is 4 kV. And I explained to you in the first slide, origin of installation 6 kV, installation category 4, inside the building, that means after the first switchboard, installation category 3, and equipments are able to withstand 4 kV. Now this lighting production standard explains the user of the electrical equipment should ensure that surges in this area is limited to a level less than 4 kV. Further, lighting production zone 2, surges less than 2.5 kV, surges less than 1.5 kV in a lesser level. So basically, if we are able to achieve the LPZ concept, we will be able to protect all the electrical and electronic equipment. And here you see, you need a surge protection device, you need one more surge protection device, you need one more surge protection device. The first one, purpose of this one is to divert the lightning current, which is in the form of 10 by 350 microseconds. That means this one, it is a very high level lightning current arrestor, lightning or a surge arrestor. So I skipped this slide also. Okay, the SPDs are called as class 1, but generally we used to call as class B, but class B is according to the old German standard, but according to IEC it is class 1, class 2 and class 3. Three kind of SPDs are required to reduce the transient voltage. So here a kind of a connection is explained. I skipped these two slides. You imagine there it's a 3-phase 4-wire network, RY phase, neutral and the earth line. You imagine that this is a distribution board, incoming and finally it goes to load. I am just trying to explain how SPD works. You imagine that there is a lightning strike and the ground potential is increasing. A lightning strike on the building, ground potential increases. That means this PE wire is going to have high potential with respect to the service incoming. Because this service is connected to a transformer maybe far away. So with respect to a service which is connected far away, we are going to have a high potential at the PE conductor. And you imagine 4 SPDs are connected, SPD 1, 2, 3, 4. SPDs are nothing but maybe a spark gap or a varistor or a diode. These are voltage operated devices. It means what's when the potential difference, you imagine that this one SPD4 is a spark gap. Spark gap. It means a spark over in a gap. There are maybe 2 plates and air in between. Once when the potential difference of the SPD between the terminals, once when it crosses certain limits, then there is a flashover. You imagine that the potential difference is, or the voltage operating or the voltage protection level is, let's say, 1 kV. High potential is created in the earth line because of lightning strike. High potential. Immediately, potential difference between PE and neutral ensures that this particular SPD is in operation. It is operated because once when the potential crosses 1 kV, there is a flashover, and due to the flashover, both the lines are connected together. Now PE and neutral are connected together. It means there is no potential difference because these two are connected together through the SPD. Immediately, there is the same potential difference will experience between neutral and the other phases. SPD 1, 2, 3 operates, and all the other lines are also connected to the neutral. And basically, what we are achieving is EQ potentialization, equal potential everywhere. And I told you, SPD is creating a kind of a short circuit situation. But now to select and install SPD, there are other conditions which need to be met. But basically, what SPD does is this. So this is another condition. I skipped this particular slide. What will happen in case of a surge in one of the line? Again, SPD3 operates, potential is transferred to PE, other 3 SPDs will operate, and finally EQ potentialization is achieved. And current sharing. Under the first condition, EQ potentialization, you imagine that in the previous one of the slide I explained that 50% current goes to ground and 50% can come inside the building. And the amount of current which is coming inside the building need to be taken out. So this SPD should be installed in such a way that the SPD is able to divert the lightning current towards the service. Instead of coming inside the building, it is diverted towards the service. So in that case, in one of the first slide I told, lightning current is maybe class level 100 K, class 1 200 K. In case of 200 K, 100 K goes to earth, and 100 K will come inside the building, and that 100 K will flow through this particular SPD. 25 K will flow through each SPD, and this is how the SPD current ratings are derived. And what kind of SPDs are there? Spark gap, varistor, diode. So spark gaps are very strong devices but little bit slow. Varistors are faster than spark gap but the energy handling capacity is limited. Diodes very fast but it can handle little energy. So the spark gap can handle lightning current, very large current. Varistor can handle small surge currents. So one of the example is you see in this particular case here. LPZ0 and LPZ1, outside to inside, a wire which is coming from outside to inside. At this place you can have a spark gap, second place you can have a resistor, and the third one you can have a diode. One example. It doesn't mean that this SPD is always a spark. No, SPD can be any technology. Only thing is it has to satisfy the conditions explained in the standard. That's all. And now, whenever we install an SPD, you imagine that you want to install an SPD in an existing panel board. There is a panel board, let's say at this place there is a panel board and you want to install an SPD. What will we do? We buy the SPD, maybe with a box, keep it outside the panel, take long wires and connect. So if we use long wires, see in this particular case, a wire in parallel from the line to SPD and from SPD to bus bar, and the maximum allowed length is, I have shown 0.5, but in the new standard it is reduced to 0.25. That means, in simple, use very short wire to connect an SPD. Thickness of the wire is not very important, but the length of the wire should be as short as possible. So you can also refer the standards SLS 1473 part 1 to 4, which talks about the first one, surge protection device connected to low voltage power distribution system, performance requirements and testing method. Part 2, selection and application principle. What SPD, which area, what about the voltage conditions are explained here. Part 3 talks about surge protection devices connected to telecom and signaling lines, performance requirement and testing method, selection and application principle. These are explained here. SLS 1496 part 1 to 7. You know the standard which I was explaining so far, the first 4 standards, because it is only explaining the total protection as a total. It is not talking about any components. The standard is okay, you can have a round conductor, maybe 10 mm dia and so on. But you need to check this particular standard, for example, requirement of connecting components, requirement of conductors and earth electrodes. So these are the substitute standards which need to be referred for selecting a component. So the standards in other parts of the world, you know, lot of our installations are with early streamer emission devices, and the suppliers always claim that it is conforming to national French standard. So you have to understand that it is not that particular NFC code is not the main standard. It is a supplement to the original standard, and even in France, the standard is NFEN 62305. Whatever I explained here is the French standard. Early streamer emission is as an added subject, as an added standard. Only the air terminal is considered, but under several conditions. So in British, BSc Engineering 62305 is standard, NFPA 780 for America, and in India now from last June onwards IS 62305 is introduced, and all these standards recommend to use conventional method, Franklin rod or Faraday cage. This is the only method explained in the standard. There is no device or method capable of modifying the natural weather-related phenomena to the extent that they can prevent lightning discharge. This is the first heading of the standard. What does it mean is, lightning is a natural phenomenon, you cannot modify it or you cannot catch it. It will flow or it can hit anywhere needed. What is possible for us is ensure that our properties are protected, people are protected. So by this, you can also note down our contact details of me and Mr. Hadi. So we didn't give the address because nowadays, mostly no one writes a letter. Letter is WhatsApp, email or SMS. Please note down. So, thank you for your attention. I hope whatever I explained is useful to you. Now we are ready for the question and answer session. So I would like to invite you to the desk.
Thank you very much. Thank you very much, Engineer Rohan. Yes, now your time. We have limited time, 15-20 minutes maximum. Yes.
Building having a power control cathodic control. With respect to these reinforcement for the structure.
Yeah. Cathodic protected foundation or a foundation which can be connected to the which can be considered as earthing, which can be corroded due to some leakage currents, or which need an additional cathodic protection is also there, but not in any of the standards which I explained. There is a method of using, sacrificial anode. So there are sacrificial anodes available. Sacrificial anode is nothing but instead of corrosion is an electrochemical process. Instead of making a corrosion in the structural steel, this sacrificial anode will corrode. So depending upon the size of foundation and the total installation, we can design a sacrificial anode system and install it for some expected time, let's say 10 years, 20 years. We can calculate and install it, and after some time you will replace it.
My question is, we used to connect these because of the reinforcement for the structural steel.
Yeah.
Then again, cathodic protection also connected with this steel. Will it be that?
No. But the question is very difficult to answer because several conditions. It is possible. But how it is possible, maybe I need half an hour to explain. So I can explain this to you after the hearing. Maybe the next question.
You can exit and
Thank you.
The residual voltage of the cell resistor and the maximum impulse withstand voltage of the equipment are they related, like the maximum impulse withstand voltage can be higher than the residual voltage?
Yes, the residual voltage of SPD including the connecting wires. Residual voltage or the voltage protection level of the SPD including connecting wires shall be at least 30% lesser than the impulse withstanding voltage of that particular area. For example, at the origin of installation or at the second level, impulse withstand is 4 kV. So you can go up to maybe 3 kV. 3 kV is the maximum limit, including connecting wires. And now you can imagine if you use a longer wire, then the effectiveness will reduce. Generally, what we do is we only look at the voltage protection level of SPD. But imagine, voltage protection level of SPD is only one of the factors. The connecting wire also need to be considered. I hope you understood. No? So, the first picture which I have shown, the origin of installation. Let's say you have a distribution board here, and the equipments of this distribution board can withstand 4 kV impulse voltage. 4 kV impulse voltage is nothing but the transient voltage which is coming across the terminals. That means you imagine this is an MCCB terminal 1, 2, 3, 1, 2, 3. So the potential difference maximum it can withstand 4 kV between these two terminals or between one terminal or metallic parts inside the MCCP with respect to its the place where it is fixed. It means the body of the panel. So if this equipment can withstand only 4 kV, how we install SPD is like neutral. From the bus bar, physically SPD is installed somewhere. From the bus bar, connecting wires are used. If the withstanding level is 4 kV, maximum you should allow is 70% of 4 kV. I mean 2.8 kV is the limit of transient voltage which is allowed inside this dB. Now this particular SPD as well as the connecting wire should reduce the potential less than 2.8 kV. Maybe you can use an SPD of 1 kV, here 1 kV and here 0.8 kV. What is determining this 1 kV is because. So this is one of the examples. If you can have a shorter wire line, you can increase the potential protection level of the SPD, then the cost of SPD goes down. I hope now it's clear. So,
what is the recommendation for the extra downconductor maybe instead of using natural conductor? The first question, and another is what is the good way for bonding the rebar of natural conductor with exothermic or plant?
exothermic is the best. Please note, exothermic is the best, but the problem is, if you imagine a building of that height, which needs thousands of connections, doing exothermic welding will be very difficult.
No, I know the downconductor extra downconductor we can use how the earth point man and the downconductor should be exothermic or plant.
That means what I understood is an existing building, you are going to erect a lightning protection system, a down conductor which is outside the building, and then you have an earthing system. How to connect the earth electrode with the down conductor? Exothermic welding or a nut bolt connection? This is the question I hope. Okay? Any connection under soil, exothermic is the best. You can also go for a nut bolt connection, but this nut bolt connection need to be protected against corrosion. So that is also explained in the standard. You have to use the special bandage, and the corrosion, the resistance of the bandage is also explained somewhere in the standard.
How about the inside of the building? Internal system, the ramp of exothermic, the inside of the concrete.
Inside concrete,
Because I have seen some downconductor arrangement in the building natural conductor by using rebars.
okay.
So the rebar line equipped with the rest point, they are using clamps. So how we can recommend for the proper?
Let me just show you that picture. This is what is recommended. I don't remember the slide number. The first one, welding, 50 mm length. This is explained for a normal tag welding. You are using a normal welding. If you are using exothermic welding, this length, the 50 mm length. See, what I mean is, in the overlap the steel conductor, a long welding is required, should be 50 mm. This class can be avoided if you do an exothermic welding, and this exothermic welding should then satisfy some points of the standard, mechanical strength, the current handling strength. Then the third one is freeze-thaw and other tests, because under maybe at 0 degree it should not break, at 50 degree it should not lose or something like that. So all those conditions it has to be. Welding is the best. Second best is a clamp. But not only the clamp including rebars need to be tested. With a lightning current, maybe 10 kiloampere, 20, 30, 50 kiloampere lightning current from so this is you imagine this is your rebar cross connection. Now there is a clamp like this. Maybe one more the back side. Now current is injected at this place and taken out from this place. Lightning current generator will produce a current which is flowing through this particular place, through the contact, and it is coming back to the generator. We can, according to the condition, maybe 30, 40, 50 kiloampere. So if we clamp on the whole unit, including the rebar, is tested for this current, then we can, I hope it's clear.
Limitation is over the rebar, extra down conductor internal of the inside of the building, instead of the natural conductors.
What is recommended is to use the naturally available rebar. But once when we explain this to the civil engineers or structural engineers, practically, theoretically it's okay, but practically once when we step into it, then there will be restrictions. People say, no, I will not allow, I have some special requirements and so on. To satisfy some of the additional requirements, we recommend, or the standard recommends to use an additional conductor. But lightning current point of view, structural steel or the rebar itself is enough. Provided it is connected with the conductors which is tested.
Say that we have a cable tree was from the ground floor to the first floor. Then we have connectivity at the rooftop where the electricity at the cable tray at the rooftop. And then we ground it at the ground level. So then the cables are attached to the cable tray. Are they vulnerable to high risk and are we increasing the risk of so keep doing like that?
I don't fully understand the question.
Say that there's a cable tray run from ground floor to rooftop, cable tray.
Yeah.
And then the roof air termination method is directly connected to the cable tray at the rooftop.
Okay.
And then at the ground, it is connected to the say that to the link it is connected.
Okay.
So
Then the question number one is, do you have additional down conductors or
Yes.
the only this cable tray is the down?
we have other ground conductors.
If you have, you just imagine, if you have several down conductors and this is only for the purpose of a bonding, maybe it works. And the sheet provided you have a closed cable tray, because if you have a closed cable tray, then the magnetic influence into the wire is a little bit reduced compared to an open cable tray. And if the cables are routed through the corners of the cable tray, then it is better. One moment, I will show you. I actually prepared two presentations here, but due to the time, I skip one. So now you have to refer these standards. Oh, sorry, I think that picture is missing here. Yeah. So you have to refer this particular standard 60364-444. This standard gives an indication in case of wires running from top to bottom, or if you have an additional metallic installation from top to bottom, whether to connect it or not. It's explained. This picture is for some other purpose, but this question is answered in this particular standard. So, any other questions?
What is the gap required in between ILM cable and power cable? Is there any gap required?
Between the power cable and the power cable and the data cable?
Yeah. No, normally ILM control we will use going forward. But power cable.
But both are kept in the same cable, right? No. Yeah. The distance depends how much length you are running parallel. So if you are using it for a short length, then distance can be less. Generally, it is not recommended to run different voltages parallel. So you have to have separation, or you have to have a kind of TEng. That is what is explained here. And the distance purely depends on the length, which both the wires are running parallel. But again, the distances are also explained in this particular section. I would recommend all engineers together, you can write to SLS, make this standard also an SLS standard. So maybe in 1 year you will get a solution. So, okay, since there are more questions, let's go to the last question.
So in a situation where we need a dedicated earthing for particular instrument, this is critical, right? So we have a building all the lighting applicants are connected to down conductors, maybe 6-7 down conductors, and in middle we have a separate instrument where it needs a separate earthing which is required by the supplier. So where to locate that particular earthing, having many other earthing points in and around the building.
Yeah. This is a very complicated question, or the answer is complicated, because this is a point of argument always. But there are solutions. For example, in some countries, for sensitive electronic equipment, let's say for example like UPS, which will create third harmonics, or the computers are creating third harmonics, neutral current is more, so before UPS or maybe after UPS we put an isolation transformer. Isolation transformer, anyway, neutral is within, after the isolation transformer, neutral is not extended, so basically there is some solution for the neutral excess current. Now the question is whether that neutral need to be connected to body or it has to be separately grounded. Very simple, it has to be connected to body. You have to refer IEEE 142. IEEE 142. So it is very clearly explained that if you connect it together, what will happen, and if you connect it separately, what will happen. But basically, we are separating different earthings, and finally we put each one we put one name. This is mother, clean air, dirty air, good air. So finally, there is only one air. This is the sense there is only one air, not several air. So connecting everything together will be the best way. But how to connect is the question. I hope you understand. So generally, it is the electronic equipment as well as the other metal, it has to be connected. The problem is if you have a load, or if you have equipment which is creating noise, which is creating unwanted noise, that noise will get coupled into the other things, and the loop currents will start creating other trouble. the way to handle is not separating the earthing. The way to handle is here. But I can explain in this chapter. I hope. Thank you.
We have a small token to appreciate our two speakers for their valuable contribution and for being us despite of their schedules. May I ask Engineer Jaycees Meegoda, President of the Institution of Engineers, to come to the stage to put us to token of appreciation. Professor Lucas. Thank you very much. Mr. Rohan, thank you very much. Thank you, Engineer Meegoda. Thank you, Professor Lucas. Thank you, Professor Rohan. Engineer Sharafi.
In late 90s, in one of our sectional committee meetings, I proposed that lightning protection seminar to be organized by IESL. The response was that it is more towards science than engineering at that time. But today, it's not only for electrical engineers, but also from the lectures, it's clear that it's not only for electrical engineers, but also for civil engineers and architects as well. So I think that you have got enough information from the detailed illustrative lecture we had today. So in that respect, I thank Professor Lucas for the colorful introduction, and for the detailed discussion I thank Engineer Gopakumar. In addition to that, our sponsors, Obo Betterman, the quality lighting products manufacturers, and they have extended their fuller support to organize this event successfully. And the secretariat staff have extended their support to organize this event as usual. And I also extend my thanks to electrical and electronic engineering sectional committee members. And finally, our sponsors have organized a cocktail for you all to enjoy. Please be present at the members lounge and enjoy the cocktail on behalf of our session committee. Thank you very much.